Hi everyone, it's Loic at Controls NYC. Last video, I showed off some of the diagrams I've made to plan for my Chrysler building BMS. This video, I'm going to go over my new diagrams I've made since then. Specifically, we're looking at my sequences of operations and my riser diagram. So first is my sequence of operations. A sequence of operations is a document that explains how the HVAC system is going to work, how all the components are going to work together, and what each component does. So some notes before we begin is that the objects in the points list will be marked with an A or a T, A meaning an alarm, and a T meaning that the data will be stored in histories, which means that it will be able to be viewed over time as a graph. So first up, we have some AAQ dampers. They're going to be controlled by actuators and modulate the airflow, and they'll remain in their last position before they were turned off. They can be modulated to increase or decrease the airflow in and out of the AAQ. They'll be modulated to allow plus or minus 25 CFM or cubic feet per minute of the set point of 1600 CFM. So all of these set points are adjustable. And what this part means is that the allowable error will be 25 CFM. I'm not sure if this is realistic. All of these specific numbers I found were based off of internet searches. So if they're very unrealistic, please let me know in the comments. So the supply and return dampers will be linked to open and close the same amount, while the mixed damper will be linked to open and close the opposite amount so that there's a constant amount of air circulating. What this means is if the supply and return are open 75%, then the mixed damper will be open at 25% so that there's 100% air circulating at all times. Next, alarms, we have the duct static pressure. If the airflow measuring station detects a flow differential greater than plus or minus 50 CFM, an alarm will occur. If the high static switch detects a pressure differential for more than 0.05 adjustable from the set point of 0.5 inches of water column, that's the pressure measurement, an alarm will occur. And the report alarm condition generated by the room pressure sensor to the BMS. So this is a pressure meter inside the room that's going to be reporting to the BMS. The points list, we have the airflow measuring station and the static pressure set point, which are both AI analog input, and these will both be linked to alarms and stored in histories. Next, we have a supply fan VFD. This modulates the airflow of the supply fan, and when it's off, there will be no air through the system. The pressure control, they'll be started from the BMS graphics and run continuously. And the VFD differential pressure falls outside of the limit by more than 0.01 inches of WC, an alarm will occur. Some alarms are fan status. So if the airflow measuring station detects an airflow differential greater than plus or minus 50 CFM, an alarm will be sent to the BMS. Basically, this means that the fan is broken, so the pressure differential, the airflow differential will be much greater on either side. And the duct static pressure, the report alarm condition generated by the RPM. The points list will be airflow measuring station and the static pressure set point, which are both AIs, linked to alarms, and histories. Next, we have the exhaust fan VFD, which works very similarly to the supply fan VFD, except it just works for the exhaust fan. I'm going to scroll through this one because it's very similar with all the same measurements. Next, we have the room pressure monitoring. So this is what I was talking about earlier, the RPM. It indicates the pressure differential between adjacent rooms in inches water column, which is a unit of pressure. If the differential pressure falls outside by more than 0.01 inches, then an alarm will occur. So the alarms, we have the high-low pressure alarm, and we have the points list, differential pressure, and the differential pressure set point. These are both AIs. The differential pressure will be linked to an alarm, but the set point will be available in histories. Humidifier will provide humidification to the space. When the system is off, the humidifier valve will be closed. It'll control humidity, so it'll be run continuously and try to keep the relative humidity within the set points of 20% and 60%. These are adjustable. Some alarms will be the high-low space relative humidity alarm and the duct relative humidity alarm. Just make sure that it stays within 5% of the set points, and if it goes over 5% for more than 15 minutes, then an alarm will be sent. Some points list are the humidifier control valve, which is an AO, an analog output, because that's the way that valves are controlled. This will be available in histories. The supply relative humidity and the space relative humidity are both AIs because these are controlled by sensors. They'll be linked to alarms. And we have a supply duct relative humidity, which will be linked to an alarm. This will not be available in histories. And next we have a dehumidifier, which removes humidification. Works very similarly to a humidifier, so I'm going to scroll through this one again because they basically control the same things. Next we have a heating coil. This heats air before it's blown through the ductwork. When the system is off, the heating valve is closed. It's going to be run continuously and try to keep the air between 60 and 78 degrees in order to maintain the air temperature at 68 degrees Fahrenheit. The allowable error will be 1 degree Fahrenheit. Next, we have some alarms. Make sure that it stays within 4 degrees Fahrenheit. If it goes over then that for 15 minutes, then an alarm will be indicated. So this will be for the space and for the supply air temperature. Next, for the points list, we have some heating coil control valve, which is an analog output, again, because it's a valve. We have an outdoor temperature sensor, we have a supply air temperature sensor, and a mixed air temperature sensor, which are all analog inputs. These will all be linked to alarms and histories. We have a cooling coil, which is very similar, except it controls cold water in order to cool the air. So again, it keeps the air within the same set points. And a VAV reheat coil, which works again very similarly. All of this is very similar to the other heating coils because they, at the end of the day, they just control water temperature. Next is the chiller. So this cools the water to send to the AHU in order to keep the temperature constant. When the system is off, the chiller is off, and the operation of multiple chillers will be coordinated with the user-adjustable graphical 7-day schedule with the holiday schedule. So this is the scheduling feature of Niagara 4. And if a malfunction occurs, then it will be switched out with the lead lag runtime object. So we'll have multiple chillers that will be switched out regularly. Next, we have a temperature control. This will be run continuously and will keep the water at around 50 degrees Fahrenheit. Again, about the numbers, I'm not sure if these are completely accurate, so please let me know if these are very wrong. That in order to keep the air at around 68 degrees, we're going to have the water at around 50 degrees. Then the allowable error will be 1 degree Fahrenheit. We'll have a high-low alarm for temperature. Make sure that it stays within 10 degrees Fahrenheit for 5 minutes. Then we have a points list of chilled water supply, chilled water return, condenser supply, and condenser return. The temperature sensors are both, they're all analog inputs, and they're both available in histories and connected to alarms. This is to make sure that the water going into and out of the chiller does not damage it by being too hot or too cold, usually too hot. Now for the chiller pump VFDs, these are going to move the water through the pipes. When the system is off, the pumps will be turned off and inactive. These will also be run on a schedule and will be switched out similar to the chillers with a lead lag runtime object. These will be controlling the water pressure and the flow. So their set point for pressure will be 70 psi with an error of 10 psi, and their flow will be 60 CFM, and their error will be 10 CFM. Again, if this is wrong, please let me know in the comments. In the alarms, we are going to have a high-low pressure alarm and a high-low flow alarm and a pump status alarm. So if it senses a pressure differential greater than 10 psi, then an alarm will be sent because this means that the pressure is no longer being conserved, so the pump is probably broken. Next in the points list, we have all of these pressure sensors and flow meters for chilled water supply and condenser supply, chilled water return, and condenser return. Next, we have the chiller control valves. These modulate water flow. When the system is off, the valves will be closed. These will also be controlled with the schedule. We're going to have the system and temperature control. They'll be run continuously. They'll open and close to ensure that the alternating use of chillers and pumps is coordinated. And they'll make sure that the supply air remains at 68 degrees Fahrenheit by allowing more or less water, turning the chiller on and off in order to heat or cool the water. The error will be, again, 1 degree Fahrenheit. Some alarms will be the high-low pressure alarm and the high-low supply air temperature alarm. The pressure alarm is just to make sure that it remains within 10 psi, make sure that the equipment doesn't break. And the supply air temperature alarm is to make sure that the supply air remains within 4 degrees for 15 minutes, just to make sure that it's not malfunctioning and giving way too cold air. Next, the points list, we have the chilled supply pressure sensor, the return pressure sensor, the condenser supply, and return pressure sensors. These are all analog inputs with the supply air temperature for this high-low supply air temperature alarm. Next, we have our outdoor units. These are going to be indoors. They're going to be on the mechanical floor, but they're called outdoor units. So they'll cool the water heading back to the condenser with a large fan. When the system is off, the outdoor units will be off and they'll be run continuously. They're making sure that the water going in is not outside of these parameters of 212 degrees Fahrenheit and 70 degrees Fahrenheit. Again, these are numbers I found online. Some alarms will be a high-low temperature alarm for the water and the fan status to make sure that the fan of the cooling unit is still working, and to make sure that the high or low temperature of the water does not damage either the cooling tower or the chiller. Next, we have the boiler. So this works pretty similarly to the cooler, so I'm going to skim through this one a little more. It's going to be coordinated with schedule. It supplies hot water to the AHU. Again, the set point will be 68 degrees, but the water provided will be 75 degrees in order to heat it. The error will be 1 degree Fahrenheit. There's going to be a high-low temperature alarm with supply and return temperature sensors. The pump VFD will move water through the pipes. They'll be scheduled and keep within 70 psi with an error of 10 and 60 CFM with an error of 10. Alarms, high-low pressure, high-low flow with a pump status, similar points lists. Next, we have the boiler control valves. These will modulate water flow with valves closed when the system is off. Again, these will be coordinating different pumps and different boilers. Next, the alarms, high-low pressure, high-low supply air temperature, similar to the chiller. Nothing really different here. The one difference for boilers is that they'll need a combustion fan because we need to supply air to them in order for them to heat the water. Then that just works like any other VFD. However, they'll modulate the airflow. When the system's off, there'll be no air. The static pressure set point will be 0.5 inches. The fan status, if it goes off by more than 0.01 inch, then an alarm will be sent, and this will be monitored by the static pressure sensor. Some combustion dampers for that fan will work very similarly to the dampers in the AHU. They'll modulate airflow, they'll remain in their last position. The set points are going to be a little different. I set it for 1000 CFM with an error of 100. Again, if this is very wrong, please let me know. This is just what I found online. And static pressure, if it detects more than 0.01 inches, an alarm will occur. And we have some static pressure set points and sensors as our points. So that basically wraps up our sequence of operations. Next is my riser diagram. I only have 3 different kinds of floors here because there's only 3 different kinds of floors on the Chrysler building. Each one, the main difference is the amount of zones and VAVs that we're going to need there. A zone is a small area where a VAV is going to have to control the temperature. So as you can see here on floor 10, we only need 10 zones or VAVs. On floor 2, we only need 18. On floor 1, we'll need 81. Each of the VAVs is connected to the AHU, which is connected to the Jace, which is a type of controller. Then the Jaces are all connected together to the server with both copper wiring and IP. And the server is going to be a BACnet IP run. Next, on floor 3, this is where I have my mechanical floor. We have LCPs, which are local control panels. So these are going to control the chilled water system or the chiller, the hot water system or the boiler, the cooling towers, which are going to be our outdoor units, even though they're going to be indoors, and our exhaust fans. So here you can see CHWP, that's our chilled water pumps. So we have 10 water pumps in our chiller system. Some of them are on the condenser, some of them are in the evaporator, but we have 10 total. Then in the hot water system or the boiler, we have 6. And this right here is the amount of chillers that we're going to have, 2. Also 2 boilers and cooling towers. We're going to have 3 of them. And all of these are linked to the different AHUs. in order to provide cold water and hot water to them. And that is basically a riser diagram. This was very difficult to learn for me because they're very busy diagrams at first, and if you don't know what you're looking at and what you're looking for, they're very difficult to replicate. Figuring out how to connect everything together was also pretty difficult, but once you know what you're supposed to do, it's not too bad. If I had to do this for all 77 floors, it would have been horrible, but I did a simplified version just for it to be easier to do and also to show. I also wanted to introduce everyone to Jade, another one of the interns here at Controls NYC. She's going to talk a little bit about what she does on a day-to-day basis.
Hi, I'm Jade. I'm now a graduate student majoring statistics in the University of Minnesota. My current role in Controls NYC is data analyst. Now I'm working on preprocessing data and do abnormal detections using our studio. My next step is to explore how to combine machine learning into my current work. If we can do that, it can help us to predict some root cause for each situation.
Thank you very much, Jade. As you might tell from this timeline, I'm a bit behind my predictions. I'm not worried about that though, because I'm confident that I'll be able to work quickly in Niagara, and I should have a basic framework down by day 18 or 19, which leaves me 6 days around for troubleshooting. That just about wraps up today's video. Remember to leave a comment if you have any help or questions. Subscribe if you'd like to see more, and I'll see you soon.